So regarding the schedule of season 2, I have a very draft schedule at this moment. So now suppose we start from the plan December the 6th, which means is the Sunday after we finish the season 1. As you can see, the second season is also made by 10 live sessions, including a test analysis. And the contents are mainly related to conceptual understanding and calculation-based topics, such as thermodynamics, including 2 parts, thermochemistry, which is slightly easier, and then thermodynamics. You can simply say thermochem focus on delta H and Q, which means the enthalpy change and the heat. Thermodynamics focus on delta G, delta S, basically the Gibbs free energy change and the entropy change. And then it's kinetics, how fast the reaction can go, what is the Rayleigh law, what is the mechanism of the reaction, how to derive the Rayleigh law, what is the mechanism of the catalyst, how does the catalyst speed up, accelerate the reaction. So there will be 2 sessions for kinetics as well, 2 for thermodynamics, and then 2 for equilibrium. Equilibrium includes general chemical equilibrium, acid-base equilibrium, precipitate, dissolution or solubility equilibrium, and maybe we'll also talk about some complex involved equilibrium. So also 2 sessions, so 6 already. And then we are going to have 2 sessions for redox and electrochem. This is pretty hard, to be honest. And then 1 more session is for fundamental organic chemistry. So we are going to cover the most fundamental and most important organic chemistry for the local exam first. Because national exam is getting crazy. They start to assess some contents which will be covered in the second semester of a 4-year of college organic chem. So this is very challenging for us to prepare because we don't have the time to teach you the whole book, which will take 1 full year, right? We only have 1 to 2 sessions. We will start here first, and then the last one will be the review and the seasonal test analysis. Do you guys have any question about the contents at this moment? Now say, what you are expected to include here, or, anything you would like to, ask or to share with me. Okay. I slightly, changed the problem sets. So, since the last problem set, the due date probably is pretty much the same day as the due date of the final test. So I will not give you a problem set 3. So I will include that contents in the final test. Hopefully this will be slightly easy for you guys. If you need, I can also make the problem set 3, but you guys can feel free to submit or not. If you submit on time, I will grade it. So it's the same idea. So it's not a big problem for me, but I feel, you guys may need more time, to work on the problem set 3. And since it's pretty much the same due date as the final test, right? Oh, by the way, for the final test, first, it's definitely optional. It's not, I will kind of, proctor you and work on the test for 2 hours. But I strongly suggest you find a 2-hour period, because anyway, you are going to take the test, right, in March. Hopefully you will take it in April, the national exam as well. So you need to practice to focus there for 2 hours or maybe even longer, right? So find a 2 hours of time by yourself, work on the test paper. If you feel good, if you want, submit and send to me. And then I can, find the problems and I can focus on the problems in the test analysis. But if none of you submit, I can still do the analysis, but it might not be very specific. I will I will choose the problems based on my understanding, which one might be challenging, which one might be confusing, which one might be critical, right? So no pressure at all. It's a self-assessment, right? So feel free to submit, feel free to not submit, okay? So this is the test and the problem sets. But right now, I'm a little bit, not very sure about what's your time schedule, what the time works the best for you guys. So basically, if you have a look at the timeline right now, if we start from December the 6th, and right now I didn't plan any class in the Christmas weekend and the New Year weekend. But I feel if we have 2 weeks with no classes, it might not be very good. Both from the knowledge refresh, right? If you kind of stop learning for a long time, your understanding will be downgraded actually. And secondly, I also want to try to finish the season 2 in middle February, which means we can save some time for season 3. Because even if you are allowed to take the digital exam, which is scheduled on March the 27th. So starting from February the 14th, actually, we have relatively limited weeks left, right? So we pretty much have 1 month, 4 weeks left. And the 4 weeks should be enough for us, like 4 sessions for kind of, a final problem solving analysis. Basically, for the last 4 sessions in season 3, what my plan is to analyze the questions, the local exam questions. And I hope at that moment, you guys can pretty much finish at least the recent 5 years of local exam. And if you have more time, feel free to work on the recent 5 years of national part 1, because they have the same scope, they have the same style, they have a shorter time, they have a higher difficulty. That is the major differences. So working on the national part 1 definitely will be very helpful for you to prepare the local exam. So I want to listen to you guys. 2 things. First one, can we have 1 class, either during the Christmas weekend or the New Year weekend? Can we? Secondly, which weekend do you prefer? If yes. Any idea from you guys? Because I don't know what's your holiday, right?
I'd say January 3rd for me.
Yeah, I prefer the
At
New Year
least.
weekend too.
Okay. Is there any objection about January 3rd, the New Year weekend? So if I didn't get any, verbal, including, voice objection or text objection, so I will change the schedule. So, shift 1 week, forward, okay? So which means we will finish it here. I will, make the change later. Okay, great, thank you. Another thing is for the extra session, which we plan to talk about the molecular orbital series and a few other stuff. So I talk with you, I want to do it in the Thanksgiving holiday. So just a final, confirmation from you guys. How many of you can make it in the Thanksgiving holiday? The Thanksgiving, I believe it's November 25th, 26th, and the 27th, from Wednesday to Friday. Is there a day which you guys can, or at least most of you can take it? Let me share my calendar with you guys, but there are some non-related stuff. So basically it's here, these 3 days, 25th, 26th, and 27th. And we already had a class scheduled on 29th. That is the plan, right? And this class will be the last class of season 1.
Could we do before Thanksgiving? Because I know for me at least, like I get out of school on Tuesday. Like that's my last day of school. So maybe Tuesday night. Because I think I might be going away from like Wednesday to Friday, or like at least till Saturday.
I see. But if we do it before here, which means we may need to find another, regular school day or weekend. I don't know how practical it is for you guys. So if we cannot make it, I can also do it in this way. So I will make around 2 hours recording and share with no student involved and share it with you guys. That also works for me. Does this work? So we don't need to struggle with the common time. It seems like we have something from the text. Sure, I think this is a good idea. So I will, choose a day in the Thanksgiving holiday. If you can make it, just join me. If you can, watch the recording. Is this fair? Okay, great. I think let's, have a tentative date. Let me see. How about we do it on Friday? For those who might, be able to make it, is this working for you guys? Or we can do it on Wednesday. Any preference? It really doesn't matter so much for me. I can. Okay, if you guys have no strong, preference, let me see. Friday is better. Okay. Okay, how about you, Agnes? Can you make it on Friday? Okay, great. So let's do it here. Not the 3 days. Let me delete it. So we still do it, 8 to 10, okay? Eastern time. Great, thank you so much. I think we can start the class today. Since we take some time to talk about, the season 2, the extra session, we kind of, start a little bit late. So we might need to end up a little bit late. I don't know why I cannot. Just give me 1 minute. No Wi-Fi is really bad. Okay, finally it's here. Okay, great. I believe all of you guys got the lecture note 3. So basically, the key topic here is intermolecular forces and different states, including liquids, gases, and solids. Each part have some difficult points, but in general, I think this packet will be relatively easier to follow compared to the first one and the second one, the lecture note 1 and lecture note 2. It's not I want to put the hard part in the beginning. It's just, this is the natural order, right? We learn atomic structures first, and then molecular structures, and then we are going to apply the molecular structures and the molecular atomic structures into the intermolecular forces. Okay, great. The first part is intermolecular forces. What is the meaning of intermolecular? Basically, is among the molecules, right? Among the molecules. So here there is a table, list all of the forces holding particles together in different species. For example, for ionic compounds, take lithium fluoride, for example. What is the force holding the particles together, holding the cations and anions? Obviously, is the bond, is the ionic bond, right? Between the cation and the anion, right? And you can see, because those bonds are pretty strong, so most ionic compounds have a relative high melting point and boiling point. Make sense? So this is a very important rule or conclusion in chemistry, which is structures determine properties. You have the strong bond, and then you have the high melting and boiling point. The bonds is the structures, and the high melting and boiling point is the properties. Make sense, right? And then the second one in metals is the metallic bonds, which is the electron C model, right? The force is the metallic bond. What are the metallic bonds? Is the strong electrostatic force in between the cation with the delocalized electron C, right? Did you remember the model we drew in the second lecture notes? Right? So those dots are the electron seeds. We call it delocalized electron seeds because the electrons are not kind of, limited by cation or by one atom. So it's called delocalized. And there are so many examples we can use. And obviously, metallic bonds is everywhere. So it's also pretty strong. So most, metals also have a relative high melting and boiling point, although there are a few exceptions. Actually, I should say a bunch of exceptions, such as the alkali metals. Alkali metals, the alkaline earth metal, basically is group 1A and group 2A, right? And there are a few like mercury, like gallium, right? There are a few stuff which are exceptions, but most of them, especially the transition metals, they all have relative high melting and boiling point. And then it's the compounds connected by covalent bonds, such as diamond. Each carbon take a sp3 hybridization, make 4 bonds with another 4 carbons, and then it turns into a network made by carbon-carbon single bonds, right? Sigma bonds, covalent bonds. So it has pretty much the highest melting and boiling point. That's because the bonds itself is strong, but there are so many bonds in the structure, right? Just too many. So diamond, graphite, they have pretty much the highest melting and boiling point, right? So basically, those 3 are typically not called intermolecular forces. Why? Because there are no molecules in these 3 types of species. Does this make sense to you? No molecules? Ionic ionic compounds? Does it have molecules? Molecules is a small group of atoms bind together, right? Do you think in lithium fluoride, one lithium cation and one fluoride is called a molecule? Any idea from you guys? Guys, feel free to turn your camera on. Actually, it will be much better from my side. I can see you guys, and you guys can answer questions at any time, right? So if you think, there are molecules like lithium fluoride, that definitely is a misunderstanding. But later we are going to show you, maybe not in this class, is in the third session of this lecture notes. We are going to show you a lot of ionic solids, and then you can see there is no single molecule made by one cation and one anion. Okay. Metals, no molecules. Covalent bond is a network, no molecules. So intermolecular forces are here. Basically, the species have to be made by real molecules like nitrogen gas, oxygen gas, HF, HCl, carbon dioxide, noble gases, all of those kind of stuff, right? They are made by molecules, right? So there are different categories of intermolecular forces. So those names probably do not make too much sense to you at this moment. I'm not sure what's your progress in AP Chem. How many of you are taking AP Chem? I remember, based on the survey, there are a bunch of you, right? Good. All of the three, who turn the camera on are taking AP Chem. Is there any correlation between, turning the camera on with taking AP Chem? What are you learning at school right now?
We just finished learning about like electrons and stuff.
Electrons?
Like the unit or next lecture note 2.
Okay. So which means, our schedule actually can be a review or maybe a little bit in advance, right? Oh, nice. How about Amelia and Siri?
We're doing thermodynamics.
Okay, obviously, you guys are using a different plan, which is not consistent with the AP curriculum recommended by the College Board. Okay. How about you, Siri?
We're doing thermodynamics as well.
Oh, okay. Did you finish those kind of atomic structure, Lewis structures, molecular structures?
We went through an overview in the beginning.
Oh, okay. Is that because teacher thought you guys already learned in honors camp?
Yeah, I think so.
Okay. Yeah, I believe Hubert is also taking AP Chem, right now.
Yeah.
What are you guys are doing right now?
Thermodynamics.
Oh, wow. Okay, I got it. Okay. We will follow our schedule, and you guys can try to connect what we are learning with what you are learning in your school. Okay. Find either a overlap, is a review, or is a pre-study, or is a reflection. It can be different situations, right? Okay. So have you heard about those stuff like London dispersion forces, dipole interaction, hydrogen bond? Good. Okay. Well, put it here. So in general, they are going to have relative lower melting and boiling point. That's because the intermolecular forces, which is commonly abbreviated as IMFs, they are much weaker than the bonds, the real bonds, no matter it's ionic or covalent or metallic. So The bonds are much stronger than intermolecular forces. So bonds are bonds. Intermolecular forces are relative weak forces to hold the molecules together. So this is why most of the gases at room temperature, you can see they are relative small molecules, such as hydrogen gas, oxygen, nitrogen, noble gases, fluorine, chlorine, carbon dioxide, all those kind of stuff, right? They are relatively small. So we are going to learn them one by one. The first one, well, we start from ion dipole forces. It's called ion dipole. Based on the name, I think it's already explained what the meaning. You have an ion, you have a polar molecule. So basically, the typical example is you dissolve an ionic compound into water. Ionic compound into water. So what will be the dipole? That would be the water molecules. What will be the ion? That is the cation and the anion, is from the ionic compound, right? For example, here, did you see any difference between the left side with the right side? Is there any difference or they are the same?
For the cation, the oxygen is touching the cation, but the hydrogen's touching the anion.
Yeah, very good point, right? And actually, this should make sense, right? Because in water molecule, as we analyzed before, due to the electronegativity between the oxygen with the two hydrogens, so the hydrogen side will carry the positive, the partial positive charge, and the oxygen will carry the partial negative charge. So if the cation is carrying the positive charge, so it will attract the negative side of the water molecules, which is the oxygen side. And here, the anion is negative, so it will attract the positive side of the water molecules, which is the hydrogen side, right? So actually, this process, which process? The cation and the anion are surrounded by a layer of water molecules is called hydration. So hydration, based on the name, because hydration means water related, it means the ions are surrounded by a layer of water molecules. And the reason why it will be surrounded is because there are ion dipole forces. Makes sense, right? This is called hydration. There is another word which is called solvation. So if the solvent is water, solvation is hydration. But if the solvent is not water, you cannot call it hydration. You have to use solvation, okay? For example, let's say you use liquid hydrogen fluoride as the solvent. So the sodium chloride can also be dissolved, or at least somehow dissolved in the liquid hydrogen fluoride. So let's say if you are asked to draw an illustration to show the solvation of sodium chloride dissolved in liquid hydrogen fluoride. So could you please take 1 minute or 30 seconds to draw the solvation? If you like, you can annotate on my screen, just to show the very brief idea. Thank you, Ashwa. Thank you, Tiffany. Ashwa, I have a question for you. So in hydrogen fluoride, are the species, mostly existed in ions or in molecules? So HF, as we discussed in lecture note 2, it is a covalent compound. So the majority of the compounds will be existed in molecular form, which is HF, although there will be a very small portion to be dissociated, right? We are going to talk about this in season 2 in equilibrium. So if we have a look at, what Tiffany Joe, so obviously he wants to show the larger atom is the fluorine, the smaller atom is the hydrogen, which makes a HF molecule right here, right? So we have several molecules, and the fluorine side is closer to the cation. Makes sense, right? So here, I think we can do something similar. So let's do it this way. But this makes sense to you? So it's a kind of, quite similar question. So just to, be aware the HF is not an ionic compound. So the majority are still molecules. Okay, let's have a look at the questions we have here. Orientation, we already answered this. Other solvent, we already gave a very good one, HF, right? Which is polar. Yeah, that's it. And then I will leave this question as your homework. Basically, there is another polar solvent, which is called DMSO. And you guys can figure it out by yourself as your homework, okay? If you guys do not have questions, I will move forward to the next page. Okay, this is called ion dipole. The second one is called dipole-dipole forces, which means the molecules are polar, right? Why polar molecules will have dipole-dipole forces? Think about, let's take HCl for example. So HCl is something like this. The hydrogen side is partially positive and the chlorine side is partially negative. So when there are several molecules, they will, line up like this. Basically, the negative side will be closer to the positive side of another molecule. And we can continue to have more stuff. And actually, this is just one-dimensional. If we want to make it two-dimensional, we can continue actually. So this one will be like this because the interaction here is also positive to negative. And then this one will be like this. So it's there, here, here, here. You can definitely draw more. It's a little bit messy. Let me, erase some stuff here. Erase the polar. And I will make it up. Does this make sense to you? If it definitely can be a three-dimensional structure, so let's say in the liquid HCl or even in the solid HCl. So those kind of interaction is called dipole-dipole forces. So basically it's still positive charge, negative charge. Do you think those kind of interaction are quite similar to the ionic bond? But why they are much weaker than the ionic bonds?
They're intermolecular rather than actual bonds.
Yeah, you talk about the key point, but why this kind of intermolecular will be much weaker than the ionic bonds? How to interpret the such a significant difference in the strength? I think based on the two diagram, you already see some differences. First one is the distance. The distance between the positive charge and the negative charge in the ionic stuff is much shorter, right? According to Coulomb's law, it will, strengthen the bonds. And another more important reason is this is the real charge. It's +1, +2, +3, -1, -2, -3. But this kind of charge is partial charge, which is much smaller than a real charge, right? It depends on the electronegativity differences. So those two factors will make the dipole-dipole forces much weaker than the ionic bonds in the ionic compounds, although the nature of those two types of interactions are pretty much the same. But this is much, much weaker. So I think dipole-dipole forces are relatively easier to understand. So I have a example. You guys can have a look and try it out. Yeah.
So if ionic forces are so strong, how is water able to break it up?
This is a very good question. Let me see. I think I have a question. You guys can work on this question first. I will find the question and show you later, okay? For you to have a better understanding about this one. Yeah, I find it. So let's finish this one first, and then we will talk about the one Amelia just asked about. I'll be right back to get some water. Okay, interesting. Why? Tiffany, would you mind to clear your drawing for the previous question? I just cannot, remove it. Every time when I try to clear it, it is back.
Wait, I'm clicking clear, but it doesn't work. I don't know what happened.
Oh, okay, it's fine. I think it's very light, so it should be okay. Okay, Tiffany, do you already have a conclusion? Which one has a higher boiling point?
I think it would be the one on top.
What's your reason? They are isomers. They have, pretty much the same, structure, definitely the same formula.
Because like, I think maybe the CLs will have like a partial charge, so it'll be easier to form like a network. I don't know.
Okay. Let me ask it in this way. So which molecule do you think is polar?
Oh, probably the one on the bottom is more polar.
Yeah, this one definitely is polar because the two dipole moment, if you add them, it will be in this direction, right? And the top one, they have the same strength, but the opposite direction. So which means this one is non-polar because it perfectly cancel out. So the bottom one is polar, the top one is non-polar. So if it's polar, this one will have the dipole-dipole interaction. This one will have no dipole-dipole interaction. So since they are isomers, we are assuming the other intermolecular forces are the same for these two molecules. So the only difference will be the first one, the top one, no dipole-dipole. The second one, having dipole-dipole. So our conclusion is the bottom one will have a higher boiling point, which is the also one. You guys can also take some notes about the OP here. That's basically, the relative relationship between two groups on the benzene ring. So if they are in this way, like anti is called para, which means they are in the opposite direction. If they are neighboring to each other, so now say like this, they are called also, although I'm not sure why it's called also. It just doesn't make too much sense for me, but I believe it's from a certain English word. If you guys know, you can tell me. So if you like this, with one carbon in between, this is called meta. So we typically use O, M, and P to show the three relationships. So this is something we are going to talk in organic chem. So our conclusion is the also one will have a higher boiling point. Let me check the boiling point for you guys. This is called also dichlorobenzene. Yeah, as you can see, the boiling point of the also dichlorobenzene is 180 degree. And then we can have a look at the para. The para one is much lower, it's 53.1, right? So it is consistent with our theoretical, analysis or prediction. So the question I want to use to answer Amelia's question is here. You guys can also have a quick look. Since it is the AP level, I don't think you guys need to take a long time. So the key point is in F, but you can quickly, go through B, C, D, E. Let's try to finish BCD first, and then we can, go over F together. Ashur, could you please, briefly talk about B?
Yeah.
You know where is sodium in the periodic table, right? Basically,
Yeah,
it's in the
it's 1s2, 2s2, and 2p6, right?
exactly, right? The 3s1 is gone, right?
Yeah.
Okay, Eddie, how about part C?
The Na ion is larger than the Li plus ion because Na has has the filled 2s and 2p orbitals.
So what? If you have the field 2s and 2p, what's the key point here?
Has more electrons.
Using principles of atomic structure, yeah, it's very close. Your answer actually is okay, but I just want to make it more specific. You see, you find the target directly. So you mentioned about, it has 2s2, 2p6. So what you want to say actually is the sodium plus has one more layer of electrons, right? So that might be more straightforward to answer the question because, one more layer means a larger size, right? Okay, Hubert, how about part D?
LICL has a greater lattice enthalpy.
Justify your answer.
Like, I think the lithium ion is smaller than the sodium ion, and the bond between like the ions in LICL are stronger than the bonds between the ions in NaCl.
Okay, I think go ahead if you have more stuff.
Yeah.
Okay, I think it's 95% correct. So what I will, further suggest is you can quote the Coulomb's law, right? They have the same charge, cations, anions, but the listen plus is smaller in size than the Na plus, which means the distance between the neighboring cation and the anion in listen chloride is smaller. And then, according to Coulomb's law, the forces will be stronger in listen chloride, and then the lattice energy will be greater. So it seems like you talk about a lot of obvious stuff, but you want to make your logic very clear. Okay, next part. Amelia, what's your idea? Which one is the listen plus? Which one is the chloride?
The chlorine is the light gray ones. And then the lithium plus are the smaller ones.
So what's your, the reason to support you to get this conclusion?
I think the Cl ion is much bigger than lithium, the lithium ion.
Makes sense, right? The chloride has 3-4 layers, and the listen plus has only one layer of electron, right? Yeah, that's exactly the point, right? Although the question doesn't ask you to give a justification, so that should be enough. And then, guys, have a quick look about part F. So keep Amelia's question in mind. Amelia was asking, so since the ionic bonds are so strong, so why the water can still dissolve it, right? Not only the water can dissolve a lot of ionic compound, it's some of the dissolution are exothermic, although some of them are endothermic. So there is a competition. The first process is to break the ions apart, which is corresponding to the lattice energy, right? Obviously, this process is endothermic because you need to break them apart, right? You need to overcome the ionic bonds. So the key point is coming. So the dissolution of lithium chloride in water is exothermic. Since the first process is endo, so which means there should be a second process which is even more exothermic, which can overcome or cancel the endothermic process and then have some net energy, released. So what you need to do is identify all particle-particle interactions that contribute significantly to the dissolution process being exothermic. So for each interaction, include the particles that interact and the specific type of intermolecular forces between those particles. Any idea?
Would it be maybe like there's a repulsion between the lithium ions and the chlorine ions or something?
But it's cation and anion. Where is the repulsion from? I think the natural result is still the attraction between the cation and anion, right?
Is there energy release from like the hydration of the...
Oh, definitely yes, right? Because that is called the ion dipole interaction. So once there is an interaction or a force, the energy will be released because the system, is making those interactions and making those forces, which will lower down the system energy, right? So the hydration process is definitely exothermic. So now I think we got a clear idea. So why some ionic solids dissolution are exothermic is because the hydration is more exothermic than the lattice energy needed to break the ions apart. But for some ionic compounds, the hydration process may not be so exothermic, so the total net energy change is still endothermic. So Hubert, can you continue to answer the question, what kind of particles are involved and what is the specific type of IMF?
The water molecules, and then the lithium ion and the chloride ion.
And the force is called
hydrogen bonds.
Wait a second.
Dipole.
Wait a second. What that force called again? Between the water molecules and the cation and the water molecules with the anion?
Dipole.
Ions is not a dipole. Dipole means one side is positive, another side is negative. So ions are just ions, either cation or anion, right? So there is no dipole in ions, in separate ions. So that is called ion dipole interaction, right? That is the first one we talk about. Make sense? So in order to further answer Amelia's question, so it seems like the ion dipole forces are not that strong. Why it can make more energy, can release more energy? Is because each cation and each anion will be surrounded by so many water molecules, right? Not just one or two. It's a lot. It depends on the size of the cation or an anion, right? So each cation and each anion will release some energy. So in total, this total energy is not small anymore. So it can overcome the lattice energy. But in order to make the dissolution process spontaneous, it's not just the heat question. There is also entropy related. So this is something we need to further explain in thermodynamics. But just give you a sense, this hydration can be very exothermic because there are so many cations and anions. Okay, if you guys are good, I will shift back to the. How about we take a 5 minutes break and then we'll restart at 9:07. Okay.
I have a quick question.
Sure.
So we said that because the second one is dipole, that's why it has a higher boiling point. But didn't we say before that dipole forces are like relatively weak and like they're not that strong? So
yeah,
why
you're
would
right. So when we say it's weaker, we are comparing it with the bonds.
Ionic? Okay.
The ionic bonds, the covalent bonds, the metallic bonds, the real bonds. But if you compare it to other intermolecular forces, so the dipole is still relatively strong. And here, since the top one has no dipole, the second one has some extra dipole. So even it's weak, but it still works, right?
Okay. Yeah.
Okay. Take a 5 minutes break. I will see you guys at 9:08. Okay. Okay, guys, I'm back. Let's continue. So there's a very brief summary. Polar molecules take part in dipole-dipole interactions. Dipole-dipole interactions are weaker than the forces between ions, which are actually not regularly called forces. They are called bonds, although we know bonds are one type of strong force, right? So typically, we just do not call them forces. We prefer to use bonds to emphasize their strong forces, okay? And dipole-dipole interaction falls off rapidly with distance because it also follow the Coulomb's law, right? Especially in the liquids and the gas phases where the molecules rotate. There's a very interesting example for you guys to have a look. Briefly explain the trends of the boiling point of the molecules listed in the left. So in order for you guys to have a better understanding, here gives the model. Any idea? Is Edward online?
Yeah.
Okay. What's your idea?
Is it because like the first few are like the first one's like non-polar, and then like as it moves forward it becomes more and more polar? So
yeah, that is the mu, right? The mu means the dipole moment. Very good point. So basically, it shows how strong the polarity is, the molecule's polarity is. So as Edward mentioned, from the left side to the right side, the molecules are getting more polar, which means the dipole-dipole interaction is getting stronger. So this is why they have a higher boiling point. But there is one more thing you need to pay attention. The molecular weight, which is the molar mass of those four molecules, are quite similar. Why we carefully choose four molecules with very similar molecular weight? There must be something behind this, right? And similarly here, we choose isomers, right? Which means they also have the same molecular weight. That's because we want to minimize, or we want to neglect the other forces. That will be the next one, and which is I think the second most complicated intermolecular forces is called London dispersion forces. London is not the name of the city, it's the name of a scientist. I forgot, it's a female or male. It's called Hydraulic London. Dispersion, what does this mean to you, dispersion? Dispersion means spreading out, something like that, right? Let's have a look. The London interaction or London dispersion forces arise from the attraction between neighboring molecules. First, let me put the keywords in the blank. It's called instantaneous dipole. This is a pretty long word. What is the meaning of instantaneous? That's not permanent. It's temporary, right? That's called instantaneous. And first, it is between the neighboring molecules. Secondly, it's between all types of molecules, no matter it's polar, non-polar. So later we are going to explain what is the meaning of instantaneous dipole. So its strength increases with the number of electrons and occurs in addition to any dipole-dipole interactions. So basically, Oh, there's one more thing. Polar molecules also attract non-polar molecules by weak dipole-induced dipole interactions. We can explain this part later. Let's talk about, what is the instantaneous dipole. So now take the noble gas, for example. So we know the noble gas is a monoatomic molecule since it's made by a single atom, right? So we know it's definitely nonpolar. But it seems like if it's nonpolar, there will be no dipole-dipole interaction. But we know, according to Heisenberg's uncertainty principle, we don't know where are the electrons. But there might be a scenario like this. So let's take helium, for example. So the two electrons at one moment is in both left. And then in another moment, they are both right. So in this case, there will be a very short-term dipole produced by the uneven distribution of the electrons. For example, in this case, the left side will be partially negative. The right side will be partially positive. In this case, it will be like this. So this is the meaning of instantaneous dipole, because it's just caused by the uneven distribution of the electrons. So first, it's very small, very small. Second, it appear and disappear very fast. Because in another time moment, it's gone, right? So think about, compared to the permanent dipole in between the polar molecules, this kind of instantaneous dipole-dipole interaction should be weaker or stronger. The first one, in between the polar molecules, is permanent dipole. And here, in between the non-polar molecules, is instantaneous dipole. So I think we can conclude this instantaneous dipole typically should be weaker than the permanent dipole-dipole interaction. So London dispersion forces are typically weak. Does this make sense to you? Okay, great. So then the second important conclusion here is strength increases with the number of electrons. Does this make sense? If there are more electrons, there will be a higher chance to produce a larger instantaneous dipole, because you might have more electrons in one side, right? So this is why London dispersion forces are proportional to the number of electrons. So basically, it's the molecular weight, because the molecular weight is typically 2 times or slightly larger than 2 times of the proton numbers. And for a neutral molecule, the number of protons equals to the number of electrons, right? So this is why molecular weight can be a direct way for you to conclude the London dispersion forces. So now, going back to this example, making all of the molecular weights approximately the same is to neglect the differences in London dispersion forces. So we can say all of those molecules will have the same or similar London dispersion forces, but their dipole-dipole interaction is getting stronger from the left side to the right side. And then we can conclude the increasement of the boiling point. Make sense to you? And here is the same. Since these two molecules, they are isomers, so obviously they have the same molecular weight. So which means we can say their London dispersion forces are also the same. So the bottom one has some extra dipole-dipole interaction. So this is why the overall intermolecular forces in the bottom molecule is stronger than that of the top molecule. This is why the boiling point is higher. And then we can briefly talk about what is called dipole and induced dipole. Basically, there is a polar molecule. Let's say like this. And then there is another non-polar molecule close to it. So this kind of dipole existed here will induce this non-polar molecule, the electron cloud, to be distorted. So the results will be like this. This molecule will be slightly distorted, and this side will be positive, this side will be negative, because this side is closer to the negative side of the polar molecule. So this is called dipole-induced dipole interaction. Does this make sense too? Okay, let me see. The next question we need to answer is why London dispersion forces are acting between all types of molecules, no matter it's polar or non-polar. That's because it is caused by the instantaneous dipole, and the instantaneous dipole are caused by the uneven distribution of electrons, right? So no matter what is the type of the molecules, there are always the uneven distribution of electrons. So there are always the instantaneous dipole, right? So there will be an extra instantaneous dipole for the polar molecules, although there are already the permanent dipoles, right? So there is another instantaneous dipole, but it's much weaker. Typically, it's much weaker than the dipole-dipole interaction. Okay, the next one is how is the London dispersion forces related to polarizability? What is the meaning of polarizability? Basically, is how strong or how easy the molecules can be polarized. What is the meaning of polarized? This is a great example of polarized. So the molecule is nonpolar, but it is affected by a polar molecule, and then it's reshaped. The electron clouds are distorted. This is exactly the meaning of polarizable, right? It's kind of, how easy it will change into polar by the external electric field. So obviously, if a molecule is more polarizable, and then it is easier to produce a larger instantaneous dipole, or it's easy to produce a larger dipole-induced dipole interaction. So the London dispersion forces will be stronger. So these two are directly proportional to each other. More polarizable, larger London dispersion forces. So obviously, the larger molecules are more polarizable compared to the smaller molecules. The less electronegative atoms are more polarizable than the more electronegative atom, because more electronegative means it attracts its electron cloud more tightly, which means it's harder to be polarized. It's harder to be affected by the other molecules. So AP can like the polarizability, this concept very much. They always prefer you answer the question from the perspective of polarizability. Okay, let me see. Yeah, my plan is to finish page number 5. I think we can make it. You guys can have a look at this question. I think the trends are pretty clear. We don't need to talk too much about the trends, but we can definitely talk about the reason, right? First, down the group, why the noble gases are having higher boiling point, why the halogens are also having higher boiling point. What's your idea, Eddie?
The larger atoms have a higher atomic radius, which means the electrons are more likely to randomly move, which causes higher.
You emphasize from the sides, but we can also talk about the number of electrons, right? A size definitely is a factor, but if we want to conclude down the group, the London dispersion forces are getting stronger, we do better, emphasize the number of electrons or the molecular weight or the polarizabilities. Although the polarizability definitely is related to the size, right? I think for halogen, it has a similar trend, right? So here I want to ask you guys to take some notes. First, all of those are still gases at room temperature. This is why they are called noble gases. So although they are getting higher in boiling point, but here it changed. Fluorine and chlorine are gases, but bromine, is a liquid, right? That is the one of the only two liquid elements in the periodic table at room temperature. Another one is mercury, a metal, and iodine is a solid. So, this clearly show you the trends. And I would like, ask you guys also pay attention to the color of all of the halogens. Let me find the picture. Those pictures are not very good. Okay, this one is good. So the top right is chlorine gas, which is a yellowish green gas. The middle one is the liquid bromine, which is a dark reddish brown liquid, but obviously is very volatile. So this is why you can see, the vapor in the container. The last one is the iodine, which is supposed to be a purple solid, but most likely it will be black because it's too dark, right? When something is too dark, it turns into black, but actually it's just, very purple. So you can see the color is getting darker and the boiling point or the melting point is getting higher. That is actually the conclusion of the increasing London dispersion forces down the group. Make sense? Fluorine gas is quite similar to chlorine gas, but the color is a little bit lighter. But all of the halogen elements are toxic, are poisonous, especially the bromine, because it's a liquid, right? It's commonly used in a chemistry lab. So when you need to operate the bromine, you need to be very, cautious about this because it's so volatile. So if you accidentally, breathe, the vapor, it can be, very, very dangerous. You guys can also take some notes and writing down the color of each, halogen elements, because, for the second topic in the USNCO, question number 7 to number 12, which is related to descriptive chemistry and laboratories. They are pretty much those kind of, trivial stuff. Students, don't like it, but it is assessed every year. Another question is here. why is the boiling point of the halogen in each period greater than the noble gas? Basically, is the comparison between here, 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 and here. How to answer this question? I know sometimes I should leave a little bit more time for you guys to, think about, but we have a lot of content to cover. So you guys need to be very focused and, when you get the time, think actively. I think I probably am too ambitious. I want to, put too many stuff in the lecture notes because those are something I think they are very good. I want to share with you guys, but time is limited. Any idea about this? Let's take the fluorine versus the neon. So neon is number 10, chlorine is number 9. If you check the molar mass, this is 20 because 10 protons, 10 neutrons. This one is 19 times 2. Basically 9 protons, 10 neutrons for each fluorine. So now, did you get the hint?
Is it because the halogens are bigger because they form like in groups of 2?
Exactly. The halogens are diatomic molecules. So multiplied by 2 is still larger than the single atom, right, of the noble gases, the monoatomic. And you can also see the gap, the boiling point difference is also getting larger. That's because the molecular weight of the single atom is also getting larger, right? So there are a bunch of stuff we can discuss. Let's have a quick look about this question. First, what is the principle to separate O2 from the air? First, let me introduce the method. First, we are going to liquidify the gas into liquid air. And then we are going to increase the temperature to make one gas boiling. So you guys can think about which gas will be firstly boiled, which means it has a lower boiling point. So the question is, which one will have a lower BP? And then it will be boiled firstly. And then we can separate the gas with the remaining liquid. Obviously, well, we don't need to check the data, but we want to use, theoretical analysis. What's your idea, guys? First, are those two molecules polar or non-polar? There's no doubt they are
Non-polar.
Yeah, right. So if they are non-polar, I think the situation is much simplified because the only intermolecular forces we need to take care is the London dispersion forces. So talking about London dispersion forces, what will be the major factor to determine the strength? Molecular weight, right? Number of electrons, right? Polarizabilities, right? They are all the same, actually. So obviously, we can conclude the nitrogen will have a lower boiling point. You guys can confirm this by yourself by checking the boiling point of each. So we will get the nitrogen into gas and the O2 plus the others remaining in the liquid air. So this is how we separate the O2 But nitrogen gas is also very important in industry because nitrogen gas can be used to synthesize the ammonia, right? O2 can be used in a lot of different situations. But if you need to use pure O2, you may need to remove the other stuff, such as the carbon dioxide, the noble gases, right? Those kind of stuff. Further, but this is not the topic here. We just want to compare N2 and O2, which one has a higher boiling point, right? And obviously, you can extend the question by yourself, such as the O2 compared to O3. So you guys can think about by yourself. Next, explain the trends in the boiling points of hydrogen halides. HCl, HBr, HI is getting higher. This is a very interesting question. First, are those molecules polar or non-polar?
Polar.
They are all polar, right? So they are polar molecules. If they are polar, so there should be two different types of IMF. The first one is the universally existed London dispersion forces, LDF. The second one is the dipole-dipole interaction. So first, let's compare the LDF first. So down the group, what is the trends of the LDF? It should be getting stronger or weaker. Down the group, should be stronger, right? Because you compare the molar mass, right? So obviously, this trend is consistent with the boiling point. And then let's have a look at the dipole interaction. The dipole-dipole interaction is proportional to the dipole moment of each molecule. So what is the trend of the dipole moment down the group? Is it getting greater or is it getting smaller?
Smaller.
Yes, it's getting smaller, right? Because the electronegativity differences actually are getting smaller. Because the chlorine is more electronegative than bromine. Bromine is more electronegative than iodine. So what is our final conclusion? So in between these two forces, which one is the dominant one? The first one is the major or the dominant one, right? And the second one actually is not so important. So guys, this is something we need to keep in mind. So this is why all of the previous examples for you to compare the dipole-dipole moment or dipole-dipole interaction are all having a similar molar mass, because when the LDF has a opposite trends with the dipole-dipole interaction, it's very hard to get the conclusion directly. So this is an example you need to memorize, or at least keep in mind. The LDF is more important. But if you have something like this, it's not so straightforward for you to compare. For example, let's say we have two molecules, carbon tetrachloride and trichloromethane. You have different names for this, but anyway, those are the two molecules. So my question is, which one do you think has a higher boiling point? I would like to listen to you, you guys, don't check the data. So let's have a guess, but the guess is based on your analysis, okay? So A will be CCl4 is higher. B will be CH3, CCl3 is higher. C is not sure. I think I can only fabricate three options. Maybe D, I can fabricate another one. they are the same, but I don't think you will choose it. What's your idea? Thanks. Missing a few more votes. Thank you. Great. I think we got pretty much everyone. Maybe one more vote if you can. Okay, let's stop here. So let me share the results with you guys. Most of you choose CHCl3. May I invite a representative to briefly talk about this if you chose B?
I chose B because CCl4 is not polar, while CHCl3 is. Even though CCl4 has a larger molecular weight, London dispersion forces aren't as strong as dipole-dipole forces.
Okay, I got your point. Let's check, okay? But I have to tell you, comparison like this are somehow very hard to predict. So in AP Chem, the question will be like this. It will tell you which one has a higher boiling point and ask you to list all of the intermolecular forces and compare their strengths. This is the AP style question. But in USNCO, it will not tell you which one has a higher boiling point and ask you to predict. You hate it, right? No one likes it because it's really experience-based. I need to use my laptop to share the screen with you guys. I think you guys can quickly check it. CCl4. Which has a boiling point of 77 degrees Celsius. Chloroform, which is CHCl3, is 61 degrees Celsius, which means the CCl4 actually is higher. So yeah, it's different from most of your prediction, but this is the fact. So which means the London dispersion forces beat the sum of the London dispersion forces plus the dipole-dipole interaction. That's because I think we can try to semi-quantitatively analyze the question. First, one chlorine versus one hydrogen. The chlorine is significantly larger than the hydrogen, right? So this is the London dispersion forces difference. A second one, this molecule actually not so polar as you expected. We can check the dipole moment. Let me see. So I will not share the screen with you, but I will share with you what is the dipole moment, okay? The dipole moment is 1.0. The bi is the unit. So it's not very strong. If you go back to those polar molecules, as you can see, they are 1.3, the bi 2.7, 3.9. So 1.0 is a relative small, dipole moment. So this is something you may need to expect, in the USNCO. But it's really hard to predict. Question, Tiffany?
Is like the molecules that have a higher molar mass are always have a higher boiling point?
Not really. It really depends. But in general, we cannot, easily conclude the dipole-dipole interaction must be stronger than the London dispersion forces. because it really depends on the difference in long dispersion forces is large or is small. If the difference is large, and then yeah, this also reminds me another AP question. Guys, let me find it. Let me think about what can be the keywords for me to search the question. My brain is not working so well. Let me try. Chlorine, ethylene, boiling point, AP Chem. Propane. Okay, I find it. So it's 2014. A few more seconds. The question will be right with you, which is here. Nice. You guys can have a look at question 6B first, okay? Which means it's here to here. Yeah, feel free to share your idea if you got any. Basically, we need to explain the propene has a lower boiling point than the vinyl chloride. The left one has a lower boiling point than the right one. You need to analyze the difference in terms of the types and the strength of the intermolecular forces present in each liquid.
I guess one would just be like, the vinyl chloride has a bigger London dispersion force because the chlorine has more electrons than the carbon.
Then
And
the CH3 group, right?
Yeah, the methyl group.
That's it. Any more stuff? So AP is very, strictly on keywords. If it asks you to analyze the difference in terms of the types, the strength of all intermolecular forces present in each liquid, which means you need to analyze all of the possible intermolecular forces. So you mentioned about the LDF here is greater than this, I agree. But are there any other IMF? So basically, what is the polarity of each molecule? How about the propene?
Would the CC bond be non-polar?
Yeah, exactly. CH bond is also pretty much non-polar. So your conclusion about propene is?
It's basically non-polar.
I agree. How about?
The CCl has is a polar bond.
Yes.
So you would have a bigger dipole moment.
I think now if you add this part, you get it for credit. So basically, the vinyl chloride has two types of intermolecular forces, LDF and dipole-dipole interaction. And the LDF is stronger than the LDF in propene, and the dipole-dipole is an extra IMF because propene is nonpolar with no dipole-dipole interaction. So obviously the sum is stronger. So this is different from the CCl4 versus the CHCl3, right? That's different from the example there because these two works on the same direction. You don't have to struggle which one play a more important role, right? Yeah, basically this is the idea. Let me see. Can you guys, quickly take a screenshot about 6A, and you can, have a look after the class, since you already, analyze this question. So I think we can finish it. And I think you got a sense about what is the style of the AP exam, right? Justification. You are expected to write down a lot. Okay, let's continue. We have one more example on this page, part C. Which one will have a higher boiling point, the N-pentane, which is this one, or the neopentane, which is this one? So first, both of these two molecules have the same formula, which is C5H12, which means they are isomers. They are isomers. So which means you don't need to worry too much about the difference of LDF caused by the different molecular weights. But they have a different molecular shape. The first one is like a zigzag, right? The second one is like a kind of a sphere, a ball. Although they both have 5 carbons and 12 hydrogens. So first, which one do you think will have a higher boiling point? And how to analyze? I think this might be too challenging. Now say, if we say the first one has a higher boiling point, what can be a good way to explain it? The zigzag one has a higher boiling point.
More of those zigzag molecules can fit in like more compact formation, so it's like harder to detach them when you boil it.
I think it makes sense, right? The zigzag can make the molecules pretty close to each other, and the sphere one actually decrease, the contact surface area with the other molecules. So this kind of trends actually are pretty much existed in all of the skeletal isomers in organic chem. Because for C5H12, there are 3 isomers actually. The first one is the zigzag one, like this. The second one is also zigzag, sorry. But there is a branch. The third one is also zigzag, but there are 2 branches. So think about, this is the sp3 carbon, which is tetrahedral. So you can imagine the last one will be like a sphere. The first one is like a long chain, although it's not a linear chain. And the second one is something in between. So you are going to expect the first one has the highest boiling point. The last one has the lowest boiling point. And then the middle one is in the middle, has a median boiling point. You guys can check it by yourself after class about the boiling point. The first one is called N-pentane. No, not pentane. What is the name? Propane, sorry. Is it propane? Yes, it's propane. The second one is called isopropane. The last one is called neopropane. Okay, I think this is the second last part of our class today, the hydrogen bonds, which is actually is pretty complicated, but well, we will simplify first. First, what are the general trends of the boiling points of most of the molecular hydrides of the p-block elements? I think if you ignore those three, all of the others give you a pretty clear trend, right? Down the group, from the second period to the third period to the fourth period to the fifth, their boiling point are getting higher down the group, which means which intermolecular forces plays a dominant role here from CH4 to SiH4 to GeH4 to SnH4, they are in the same group. And then here, pH3 to ASH3 to SbH3, HCl to HBr to HI, H2S, H2Se, H2Te, they are all increasing down the group. So which means the LDF is the key factor here, right? Okay, down the group, the LDF definitely is increasing, but the dipole-dipole interaction actually decreasing, right? As we mentioned before in the hydrogen halogens, hydrogen halides, the HX. But obviously you see three exceptions in the second period: water, HF, and ammonia. So why? So this is the key point here, hydrogen bonds. So we need to talk about what is hydrogen bonds. Hydrogen bonds are made by hydrogen donor and hydrogen acceptor. What is a hydrogen donor? It is a hydrogen atom which is connected to NOF, either nitrogen, oxygen, or fluorine. So this one will be a donor. And what is an acceptor is another NOF. So the dashed line in between the donor and the acceptor is called hydrogen bonds. But guys, the hydrogen bonds are not real bonds. It's still intermolecular forces. The reason why it gets the name of bonds is because it's stronger than most of the other intermolecular forces. So it's something in between the IMF and the real bonds. But it's still much weaker than the real bonds, but is stronger than the other long-distance dispersion forces, dipole-dipole interaction. So for this case, I can pretty much conclude the hydrogen bonds are stronger than the other intermolecular forces because it's so special. So I think we answer which one is the donor. Donor means a hydrogen connected to N or O or F. You need to have such a hydrogen. A hydrogen acceptor is another N or O or F. So the hydrogen bond is in between the hydrogen donor and the hydrogen acceptor, donor, acceptor. And the second question is the HO covalent bond, which is here, and the HO hydrogen bond, which is here. Which one do you think is longer or shorter? I think based on the figure is already pretty clear, right? The hydrogen bond is longer. How to interpret this? It's still not
it's longer because it's not actually physically connected. It's not physically bonded completely.
Exactly, right? It's still, in between the molecules is a intermolecular forces, is not a real bonds. It's not physically bonded with each other. And then I need to talk about what is the nature of the hydrogen bonds? Why we need to have the NOF? What is the common character of the NOF? First, they are very electronegative. This is very important. Secondly, They are small in size. NOF are the most 3 electronegative atoms in the whole periodic table. Their electronegativity 4.0, 3.5, 3.0. Another one which is comparable to the NOF is chlorine, which is also 3.0, but it's too large. The size is too large. So this is why chlorine typically is not making hydrogen bonds. So when a hydrogen connected to N or O or F, this hydrogen will be very positive. First, it is connected to the most electronegative atom, which will make the hydrogen pretty much like a proton. Hydrogen is a proton plus 1 electron, and then this electron is pretty much gone because it's so close to the very electronegative NOF. So this hydrogen is pretty much like a proton. We call it like a naked proton because the electron is gone. It's pretty much gone. So we have a very strong dipole moment here. And then another NOF, which is also very electronegative and very small in size, so it's also very negative. So a very positive hydrogen with another very negative NOF, they will have the strongest dipole-dipole interaction. And they got a special name, hydrogen bonds. But the nature of hydrogen bonds actually are much more complicated than this. So even in the 21st century, there are still publications about hydrogen bonds. It's not, we found a new type of hydrogen bond. It's just, we are still working on what is the nature of hydrogen bonds. So from my analysis, it seems like it's a special type or a enhanced version of dipole-dipole interaction. But actually, it's more complicated because the hydrogen bonds actually have orientations. For example, in the solid HF, the hydrogen bonds are zigzag. It's like this. So this is very interesting. Why there is an angle in this way? And this angle actually is consistent with the distribution of the 3 lone pairs on fluorine. So which means, when the hydrogen bond is making, it's in between the positive hydrogen with the negative fluorine, but more specifically, it needs to be kind of, working with the lone pair or one lone pair on the NOF. And this can be further demonstrated by the hydrogen bonds in water. I need to find the picture here, which is on page 11 on your lecture notes. The dashed line here are the hydrogen bonds in water. So you can see each water molecules are making 4 hydrogen bonds. And it's pretty much a perfect tetrahedral. So which means the lone pair here, the lone pair here is working, right? Donor, acceptor, donor, and this is the donor, this is the acceptor, acceptor, donor. So it has a certain orientation. So this is like the covalent bond actually, because covalent bonds need to pair the electrons, overlap the atomic orbitals, right? Anyway, what I want to share with you is hydrogen bond is more complicated than what we learned, okay? Guys, let's have a quick check. Which of the following intermolecular links can be made by hydrogen bond? First one, yes or no? CH3 and H2. Basically, you just need to figure out, is there any hydrogen acceptors? Is there any hydrogen donors? Answer is yes, right? You can find a donor and acceptor. Let me know if you have question, okay? I didn't draw it out. How about the second one? Yes or no? If it's no, let me know which part is missing, the donor or the acceptor. So it seems like I'm strongly, implying there's no hydrogen bonds. Why no hydrogen bonds? Which piece is missing? There's no donor because all of the hydrogens are connected to the carbon, which is not electronegative enough to make this hydrogen very positive. So although you have the acceptor, but there's no donor. So no hydrogen bond here. How about this one? HBr, HBr. I think this is easy to say, right? The bromine is not high electronegativity enough. The next one, let me show the connection of the molecule to you guys. This is called acetaldehyde. Yes or no? No hydrogen bond. Which part is missing? No donor, right? This hydrogen is connected to the carbon as well. CH3, you never need to think about, right? The last question is a little bit tricky. Let's say A is yes, B is no, okay? Let's guess your opinion. Okay, got your idea. Most of you think there is hydrogen bonds. The answer is yes. Where is the hydrogen bonds? Here is the hydrogen bond. The donor is from the water. The acceptor is from the acetaldehyde. Make sense? So the next question perfectly explained. So the acetaldehyde has a boiling point of 20 degrees Celsius, which is much lower than the ethanol, 78 degrees Celsius. But if you compare the molecular weight of these two molecules, they are approximately the same, right? But why there is a huge difference in boiling point? Or we can ask the question this way: why ethanol has such a high boiling point? That is the hydrogen bonds among the ethanol molecules, right? And here, no hydrogen bonds among the molecules. But both of these two molecules are miscible with water. You guys know what is the meaning of miscible, right? Which means it can mix with water in any ratio. So how to explain both of them are perfectly soluble in water? Typically,
both of them are polar. Oh,
yeah, go ahead.
since both of them are polar, they're already more miscible in water because like water separates their dipoles.
That's a good point, but it's not enough for a polar molecules to be miscible with water, because if it's polar, we can say it's easy to dissolve in water. But in order to explain it's miscible, we need to have something else. Miscible basically means, okay, there is a spy, kind of hidden in the normal people, the good people, but this spy looks like pretty much the same as the good people, and then it can hide there and cannot be differentiated by the others. So basically, the quick answer is both can make hydrogen bonds with water. So this is why they are both miscible with water. But CH3, CH4 itself has no hydrogen bond. So this is why its boiling point is pretty low. Does this make sense to you guys? I think this is the perfect example for the molecule itself cannot make hydrogen bond, but it can make hydrogen bond with water. So it has a lower boiling point, but a very good solubility in water. I like this example a lot. Okay, let's have a quick summary. Hydrogen bonding, which occurs when hydrogen atoms are bonded to N, O, or F atoms. Common characters: very electronactive, very small in size. Is the strongest type of intramolecular interaction. So we answer this question. Let me see. I will leave this question as your homework because it will take some time since there is some calculation related parts, but it's a very good question. Please, work on this. How about we end our class at 10:15? If you have to go, just free to go. Ask me for the recording, right? You can directly go to the last, 10 or 15 minutes if you missed that. I want to quickly talk about the difference between intermolecular hydrogen bonds and intramolecular hydrogen bonds. Inter means is among the molecules, intra means is inside the molecule, right? So basically here, there is something called also nitrophenol and para-nitrophenol. So I think the question is too hard. I should say the para-nitrophenol has a much higher boiling point than the also nitrophenol. And then we need to explain why. First, in the para-nitrophenol, do you think there are intermolecular hydrogen bonds, or the regular hydrogen bonds, I should say? Because when we say hydrogen bonds, we are talking about the hydrogen bonds among the molecules. So, yes or no? Hydrogen bonds in the para-nitrophenol among the nitrophenol molecules? Hydrogen donor? Yes or no? Here, right? Hydrogen acceptor? Both the oxygen and the oxygen in the nitro group, right? So which means so you can make the chain much longer, right? Make sense? Okay. And here, if we show the structure in a good way, I think you will be able to figure out something very special. This is called the intramolecular hydrogen bonds. This is a very special example, guys. Just pay attention. So think about, if the molecules can make intramolecular hydrogen bonds, it will increase the boiling point or decrease the boiling point. It will absolutely decrease the boiling point, because when the hydrogens, acceptors, and donors making the intramolecular hydrogen bond, it loses the opportunity to make intermolecular hydrogen bonds, right? So it will kind of weaken the intermolecular hydrogen bonds since the intramolecular hydrogen bonds are made. So this is why the left one has a much lower boiling point than the right one. Just give you an example. Any question about the intramolecular hydrogen bonds? This is not something very common, but it existed. Hydrogen bonds are very, very important, in chemistry and also in biology. Pretty much all of the macrobiological molecules have hydrogen bonds, DNA, RNA, ATCG, right? Hydrogen bonds to make a double helix structure. Protein, peptides, hydrogen bond, alpha helix, beta sheets. Yeah, a lot of other examples. And hydrogen bonds are so critical to our life. No hydrogen bonds, no life, actually. Because if there's no hydrogen bonds in water, water's boiling point will be as low as negative something degrees Celsius, which means there will be no liquid water in Earth. If there's no hydrogen bonds, the ice will not float on the water, which means all of the living stuff, underneath will be just that. We can talk about the application of hydrogen bonds next time, but I want to have a brief summary here. Basically, if you need to analyze the type of IMF, first you analyze what are the particles, interacted with each other. If there are only ions, it will be ionic bonding, right? If it's ions plus polar molecules, it will be ion dipole forces. Basically, it's the dissolution of ionic compounds in water or in other polar solvent. If there are no ions, and then you analyze the polarity of the molecules. If they are all nonpolar, it's London dispersion forces only. If one is polar, another one is nonpolar, there will be dipole-induced dipole forces. If both are polar, there will be dipole-dipole forces. But if there are hydrogens bonded to NOF, there will be a special type called hydrogen bonds. So this is the first part of the summary, basically list, how to analyze the IMF. The second part is here is the strength. London dispersion forces has a pretty large range of strength, 0.1 to 30 kilojoule per mole. So which means it can be very weak. It can also be pretty strong, relatively strong. Dipole-dipole, 2 to 15. So this is why some London dispersion forces can be stronger than dipole-dipole interactions. Hydrogen bonds is pretty much unbeatable, 10 to 40 kilojoule per mole. It's pretty strong. Ion dipole, greater than 50 kilojoule per mole. And then there are so many. So this is why the ion dipole interaction can be very strong. So you guys can finish this table as your homework. So basically, let's give you one example, okay? So atoms like neon and argon, there will be London dispersion forces only because it's nonpolar. So no dipole-dipole, no hydrogen bonds, no ion dipole. And then you guys can work on the other columns by yourself. Okay, guys, we used a little bit more time compared to our other sessions. I hope you got a good understanding about the session today. I think they are relative, easy to follow, but it will take some time for you to fully digest and be, an expert in analyzing questions like this, because there are a lot of factors you need to summarize by yourself. Or will take some time to have a quick review in the beginning of our next session. You guys are definitely recommended to do some pre-reading if you have time. I think the contents of next session will be slightly harder than today. Let me see. Yeah, and then the last part is okay, actually. It's relatively okay. I will share the problem set with you as soon as possible. Okay, guys, let's stop here and enjoy the remaining of your night. And I will see you next Sunday. Okay.
Thank you.
No problem.
Thank you.
Thank you,
Thank you.
Amelia. Bye, bye, guys.